All right, in this video, I want to talk about how to interpret r squared, okay, which is sometimes written as r squared, same thing. And to talk about this, I want to start by talking about how to interpret variability, and then we'll build up to how to interpret the r squared that you see when you have done a linear regression. Okay, so starting with how to interpret variability, let's take a few moments to talk about that first. Suppose I'm interested in knowing something about the weight of a 1-year-old boy. Okay, not all 1-year-old boys weigh exactly the same amount. All right, there's a variation there. Some weigh less, some weigh more. Okay, now if I'm interested in knowing something about how much does a 1-year-old boy weigh, then I can go out and get a random sample from my population and see how much do they weigh. So that's what I've done. I have 10 observations here, okay, and I calculated their sample mean, I calculated their sample variance, and the sample standard deviation. Okay, so to kind of help talk about this, I want to kind of draw this data on a number line. All right, so I have written down here, you can visualize this as a number line here. Okay, so where is my sample mean? My sample mean is slightly above 24. All right, now let's go and let's mark where our data is. So we have one observation at 20, one at 25, one at 18, one at 24, another one at 18, one at 25, 26, 27, 28, and 30. All right, so it's a relatively small sample, so I can kind of visualize the data quickly like this, right? And so what is variability? What are these numbers? We can see the mean is here in the center. A lot of times students kind of get that. It makes sense when an average is. But what are these numbers? They have to do with the spread of the data, okay? So, when you're calculating them, of course we used Excel just to automatically calculate it for us. But what's happening is basically we calculate this distance. Let me mark it in red. The distance each observation is from the mean, okay? So we calculate the distance from the mean, and then because we don't care about it being positive or negative, that's why we square that distance, and then we basically find the average of that square distance, which is what variance is, and then we take the square root so that we're able to interpret it, which is what standard deviation is. So roughly speaking, and this isn't exactly the right way to interpret this, but roughly speaking, standard deviation is the average distance from the mean. All right, and this is usually how people will kind of think of standard deviation. So in this example, we would say, okay, so the weights for 1-year-olds, 1-year-old boys are 4.1 pounds above our on average, right? Because you've averaged it out. So our on average 4.1 pounds above and below what mean is, which is 24.1 pounds. Okay, so weights for 1-year-old boys are on average, right? Because some are much more, some are much less above and below the mean. So they are on average 4.1 pounds above and below our sample mean, which is 24.1. Okay, so that's like basically explaining the spread of this data. This how much above and below the mean are these data. Okay, now why is it that some boys weigh less and some boys weigh more? How can I explain that variability? That's where regression comes in. All right, so that's the key to this whole message. Regression is going to explain that variability. All right, let me say that again because that's really important. Regression is going to explain why all these children don't weigh exactly the same amount. All right, we are trying to figure out why there's variability in our data. All right, so suppose, for example, I used height, and I use height as my independent variable, and weight as my dependent variable. All right, and so now height is going to explain that variability in weight, right? And we can see here, I've plotted weight and height, and you can see that height is explaining some of that variability, right? Not all of it. If height explained the weight exactly, then all of these points, I would say, oh, give me a height, I'll tell you exactly what the weight is, right? They would line up exactly in a line. My data would just be right in a line, right? But of course, they're not exactly in a line. So height is not exactly explaining why there's differences in weight, right? And maybe, theoretically, if I had, additional X values, I might be able to do better and better at figuring out why are these boys not weighing the same thing, right? I might be able to do better if I had additional independent variables, okay? But how good is height doing at explaining weight? All right. Since these data aren't lining up exactly on the line, still there does appear to be some explanation that height is providing for why these different weights are occurring. How well is it doing? All right, and that's where the idea of R squared comes in. Okay, so R squared tells us the percent of variability in Y that is explained, right, by the regression. Right, and by the regression, I mean whatever your X variables are. Okay, so in this case, let's see what our R squared was. Our R squared is here. It is 22%, right? We can convert that to a percentage using this little number here, and then change it, how many decimals you want, okay? So I'll do, 22.4% of the variability in weight, okay? So the variability in weight that I want to be explaining. So 22.4% of the variability in weight is explained by height. All right, that is how we interpret that R squared value, right? So we have all this variation. How am I going to explain it? I can use regression to explain that variation. And the percent of variation that was explained by that regression is given to us by that R squared value, right? And is 22%, is that a good amount of variation to be explained? Not really, right? Ideally, we want 100% of the variation in weight to be explained by our regression. That would be amazing. If all of my data lined up perfectly in a line, you could tell me the height of your child and I'll tell you exactly how much they weigh, right? That would be ideal. So 100% or an R squared that is 1 means exact relationship, right? You never see this in statistics, but you can get close to it. And the closer you are to 1, the better. Now, when R is 0, that means that basically the regression did no good. X did not explain any variability in Y. Right? And the way that would look in that situation, if R squared is 0, so here, let me write R squared equals 0. Your data would just be completely random looking, right? If your R squared is 1, then your data will line up exactly on a line, right? So this is good. You want your regression to explain the variability in Y. That's basically why you did the regression. So that's considered a good thing. Closer and closer to 1 is best, right? Now, if R squared is 0, then that means basically your regression did nothing for you. Okay. All right. And we can see a lot of times. So here, this p-value is not significant, and that makes sense because not significant meaning it is not less than 0.05. So height basically is not a significant predictor, right? Which makes sense because our R squared is also not that great. All right, and this is made up data, so that might be why that happened. All right, thank you for listening.